Hi students, Saxon 1, I'm back for lesson 81. Crisis averted. She was not in the trash, she was just scrambling around after one of her rawhide chew bones that was underneath the couch. So, everything's fine. This is the right answer. This one, we got lucky because number 1, John made the equations ready to graph, and number 2, we came out exactly on that point, although my line doesn't look like it. I just missed it. So that one worked out pretty well. We got a nice clean answer. But, sad to say, it's not always so perfect. Let's see how many examples there are. 1, 2, 3. There's 5, you guys. That's all right. It'll be fine. Okay, the next one tells us to solve by graphing. That was the same the first one said. But this looks This looks weird. I'm sorry. Y equals x. Look, these do not look like normal systems of equations, do they? That looks weird. Those equations look really weird. But we remember, oh yeah, sometimes when they're weird, they're easier to graph than we think. The first one, y equals 2. Okay, so we go to 2, and we go, okay, so no matter what value we have for x, no matter how this changes, y is always 2. So we can draw that like this. It seems hard, but it's actually easier. Now this one is one you'll remember after you do it a few times. Y equals x. What that means is that if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. And it goes right in the middle like that. You'll memorize this one. Okay, when y equals x, it's right in the middle. Front and back. Okay, now again, this one's pretty easy because we can see where the point of intersection is. It's right there. It's at point 2, 2, right? Y is equal to 2 and y is equal to x. Okay, so that one's pretty easy. Got that one right. Let's try another one. I feel like John's lobbing us some real softballs here. All right, now he's going to show us drama. Y equals x plus 2, y equals x minus 1. Okay, it's a system of equations. We graph it. He put it into y equals mx plus b format for us. He's a buddy and a pal. Okay, we go to the y-intercept to start. There's y equals 2. And then there's no slope. So we'll put 1 in. I mean, there is a slope. It's just not written down. It's invisible. So it's 1 over 1. So it's those 2 points, right? Okay, so far so good. That looks good. Now let's do this one. This time our y-intercept is -1. That's right there. And our slope is the same, 1 over 1. Boom, boom. Now look what happens to our line. What? Pretend that's straight. It's not, but it should be. Look what happens. We have parallel lines here. At this one and the other one, we had one place where the 2 lines intersected. On this one, the lines are parallel. And I'm going to write the symbol. That's not 11, that's parallel. The lines are parallel, so there is no solution. And we have a special name for parallel lines that do not give us a solution. We call them inconsistent equations, which is just a fancy way of saying there's no solution because the lines are parallel, okay? So, ooh, math vocabulary words for the win. That's all it means, okay? Good to know. Good to know. And then John goes into another section on inconsistent equations, and he gives us another problem on this specific topic of parallel lines / inconsistent equations. He gives us a problem that says, determine whether the following set of equations have a common solution. That would be, the 1 point, like we've seen in the past. So he gives us these 2 equations. Now he doesn't ask us to graph it. He just asks us to determine if there's a solution. Okay? So there's an easy way to do that. That's way easier than going into all the trouble of graphing. To determine if there is a solution, do this. Do you see how these are both equal to y? So we can just say x plus 2 equals x minus 1. This is the test, okay? That should have a colon there. So we're going to try and solve this system by a special kind of substitution in which we recognize, okay, if these are both y, then, and these are supposed to be equal to each other, then that should be equal to that. But we can quickly see, oh look, if we subtract x from both sides, we get 2 equals minus 1. Wah, wah, no. Not okay, right? So that tells us, because this is false, that tells us this is an inconsistent system of equations, which is the same thing that we said last time. Last time I just said inconsistent equations. This time I gave you the full $50 version of the answer. It's the same thing. Okay, so inconsistent means the lines are parallel. And as you can see, it's the same system we had last time. We could have known that. We just came to our conclusion using a different method that was easier than drawing the picture. Or, well, I mean, maybe you think that's easy too. It is, let's be honest. Okay, so inconsistent means the lines are parallel. They're never going to touch. There's nothing these guys have in common. Okay, so the first scenario was what we're used to, where we get 1 point of intersection. Okay, there's 1 point. This was a 1-pointer as well, even though it had these freaky looking equations. It got the 1 point that we were used to. Then we did 2 that were inconsistent systems. So they were parallel and they never touched, and they never will, you guys. And then the third kind is almost hard to explain. Let me show you a system, an example of this. Y equals x plus 2, 2y equals 2x plus 4. Let's say that's our system of equations, and we are asked to tell what kind of a graph it's going to make. Here's what we can realize. This, if we divide every one of these by 2, that's what we'll get. It's the same. So in this third type, let me just put numbers on them because that will be easier to remember. Okay, the first type was when we had 1 point of intersection. The second type was when we had inconsistent equations because the lines were parallel. And the third type, sorry, I feel better when I number things. The third type are called equivalent equations, because that's what we found, right? Is that they look different at first, but when we did a little algebra on this one, we found out they're exact same equations. This means it's the very same line. The two equations create the very same line. And so all of the solutions for this one are the same as all of the solutions are that one. Okay, so that's what's special about this third category. They're called dependent equations. I'm going to summarize all of this in just a minute. Okay, so the last example is determine whether the following set of equations is dependent. Y minus x equals 2. It's the same, pretty much the same equation as before. All you do is pretending that we didn't already know. I mean, it's really just the same as this. I'm not sure why John made this a separate example. You just look at it and try to clean up whichever one looks like it could be simplified. I see all the 2's and I go, oh, okay, well, let's divide the 2's out. That's how I knew to do that. You just look at them and kind of simplify whichever one could be simplified. And then you get, and notice in this one, I don't even have them in proper y equals mx plus b order, but it doesn't matter. As long as they come out to be the same, you know they're the same. All right, so I want to simplify, summarize, that's a better word. We talked about 3 different kinds of equations in this lesson. We talked about our old friends that have one point of solution. These are the ones we see all the time, and we call those consistent. That's their fancy name. We talked about lines that are parallel. They have no solution. They never touch each other. And we call those inconsistent. And then we have a third scenario here. Let me put arrowheads on here. That helps you see the lines separate from the graphs. And then our third one, and I'm going to draw it so it looks like 2 separate lines, but it's really not. I mean for it to be the same line, and those are called dependent. Okay, so 3 fancy words to summarize the 3 different types of systems that we might encounter, all right? We're not going to use these words a lot, but understanding the 3 different pictures is really important, and being able to identify what looks special about these 2 equations that triggers you to knowing that you've got a weird scenario on your hands, all right? So that's why John asks us questions about determine if it's inconsistent or determine if it's dependent, because we want to be able to quickly test and basically flush out the weirdos, right? The vast majority of our time is spent on these. All right, now you know what's useful about graphing as a means for solving a system of equations. And you have a better understanding about how by looking at the picture of the graph, we can learn important things about what kind of a system it is. That is the end of Dearly Beloved Lesson 81. I hope you enjoyed it, and I will see you next time.